Welcome back to my channel. I'm Brian Kafke, and I am a data and AI enabler, and this is a series called Master Databricks and Apache Spark. This is lesson 5, using the data science process. Let's jump in. I want to start out by talking about a couple of things before I get into the actual content. One is, this is a key video in that it's laying the sort of overarching steps we're going to be going through and that are typically done in any kind of data science, data analytics project. So I want to lay that out. We're also going to be bringing in another video, a use case, which is going to lay out a sort of simulated real world project, which will allow us to shape our work. And the idea behind this is that by walking through steps that you would really do in a project, you'll have a better idea how to apply this in your job and when to do what. Because I think a lot of times that's probably the confusing part, right? Like, what do I do? What should I be doing at each stage? Especially if you're new to this sort of area. On the lower left-hand corner, a little plug for my book. Published a book called Master Azure Databricks Step by Step, which is available on Amazon. Great book, very thorough. It's a big book. My daughter said I should have divided it into multiple books because it's very long, which is why it's not available currently in the print edition, but it does have extensive use case, all kinds of content, very in-depth. I have a copy myself. I bought a copy just so I could really check it out as a reader would, and I love it. So let's jump in here. What is the data science process is the first thing I'll talk about. Then I'll talk about the steps in the process, and then we'll kind of walk through in more detail, understanding the steps. Now, I do want to mention this is not a very rigid thing. This is not something that everyone will agree with. So if you go online and you Google this or whatever, you'll find somewhat different versions of this. This is the one I think that kind of applies generally, so it is a bit personal in the sense that I've adapted it to be what I think it fits best. So bear that in mind. Not everyone may agree with all these steps. Let's start off by talking about, like, okay, what do I mean by the data science process? The idea behind this is it provides a sort of framework or a structure, or even just call it a list of steps to say, what do you do? It's like if you're going to go shopping, you have a list of things you got to get. It's a similar thing. You need to do a project. The business wants you to do some analysis and maybe come up with a predictive model, like predicting forecasting sales or predicting what are fraudulent transactions coming into a system or any kind of things. And so it starts off with this sort of business problem, but then you have to say, okay, so where do I start? What do I do first? Then what do I do second? And this framework fits into a sort of data science team where individuals can do this as part of each one having more of a specialty, or it can be done by one person if it's a smaller project. So that's the first thing. The steps can be, depending on where you are in this process, iterative, and very often are iterative. And this is one of the things that's very different from developing, say, a web app or mobile app, because those tend to be, you build it, you kind of go through, and you deploy it, and then it really goes into sort of a maintenance mode. But this, even the development process is exploratory and iterative. And I do include machine learning. This may or may not apply in all use cases. For instance, you may just have a goal of exploring and providing some valuable insights, which could be displayed in, say, a Power BI, Tableau, or some sort of a dashboard, or even Jupyter Notebooks, which is providing good information like, where do our customers come from? What are our trends? What might be beneficial to change because we can see maybe we're losing customer churn and we're losing customers. And even without a predictive model, we can get valuable insights that say, wow, whenever we close the store at 5 o'clock instead of 6 o'clock, we lose like 20% sales because guess what? Most of our customers seem to be buying things between 5 and 6. So these insights can be useful in and of themselves. And I think it's really shortchanging this a good deal when you just say machine learning only, because the really analytics, we've expanded in sort of an concentric circles kind of thing, getting bigger and bigger in what we include. But business intelligence has been around a long time, and most of what we talk about has already been in business intelligence, but we've extended it to include AI, machine learning, and the like. So let's walk through the steps of the data science process, make it sound official. First, we have analysis. And the first step in the analysis stage, which is really any IT project, really should be, what are we trying to do? What's the use case? What's the business problem? Typically, in my experience, this is something like someone at the top of a company. Small company, it could be the CEO or president. Smaller companies, it could be like a division head, like the CFO, chief financial officer, somebody saying, I want to solve this problem. And so they create a project and they go through whatever the process is, and it gets into somebody in IT saying, okay, come in here, Brian, Mary, Joe, this is what we got to do and solve the problem. So that's the use case. Somebody's identifying the use case, and the use case may be very broad. And as a consultant, it typically comes into me, any kind of problem, very vaguely stated. It's not clear what we're trying to do yet. That's the first starting point. It's the tip of an iceberg in a way. Once you get that, you go through some analysis around the use case, and then you need to identify what is the data required. We'll talk more about that. So that's the analysis. You're getting kind of the basic requirements. The next stage, and you might have in that stage a business analyst or somebody like a domain expert analyst to do that and spec out a lot of things, which is nice if it's a large project. Analysts can be extremely helpful to really provide the guidance and underlying sort of direction. After that, you have data engineering. Now, for me, this is really the core of what I focus on. If you look at my videos, a lot of data engineering focus. And here we have data collection. So you have some sense. Somebody said the data is here, here, here. Maybe you don't have a clear idea, a general sense, so you have to go get the data from wherever it is, find out where it is. That helps. Then you're going to have to prepare the data for use, and then you're going to go into something called, typically, exploratory data analysis, which really is just what it sounds like. You get all this data. What does it mean? Can we see any trends? Can we connect the data in a way that's really meaningful and get any insights from it? So what can we learn about the data before we even try to do anything specific? This can be an extremely valuable phase. As I mentioned, in and of itself can be extremely valuable because you may find some really interesting insights that could identify things that the business is doing and might avoid losing customers, or might do something again that could maybe generate more sales. Like, wow, whenever we have noticed this pattern in the data, whenever we have a 10% sale during the summer, our sales jump like 30%. And you realize we can afford to do those. Maybe we should try more of those. So those are the kinds of things you can see pretty easily, typically in data. Now, once you get through the EDA, exploratory data analysis, as you call it, there's the feature engineering part of it. And I am aggregating these things, and there's no clear breaking point between some of these. But feature engineering is when you want to create a machine learning model, and we'll say predictive model. In this case, it's a little more clear talking about this, but a predictive model is predicting something like we're going to predict what will future sales be. So we know what the sales have been in the past, but we want to predict what are the future sales going to look like. Or maybe we want to do something like identifying transactions that are coming into our system that may be fraudulent. Another example might be we want to, in one case we may get very close to, we want to predict based on a customer maybe in our system or talking to a sales rep, what's the product they're most likely to buy based on maybe demographics and things. In feature engineering, we need to find out what columns and attributes drive the model. Like, what do we need to put into that model, and how do we build those features? And I'll talk a little more about that. And finally, the stage that a lot of people like, typically the machine learning stage is not something a data engineer would do. It's usually handled by a data scientist. And I do have a bit of honestly, a pet peeve, I'll be honest, that many people nowadays call themselves data scientists. And I think it's a bit confusing. And I have a personal belief that when you say data scientist, you really should probably have like a master's or PhD in statistics. And I say that because you're the expert on what models to use, on how to perhaps sample data, on how to measure the results of the model and say is it effective or not, on how to query the model and say what's driving this model so you can interpret what the model is doing, why, and how. And there are many model frameworks, so it's not a trivial task. So I know a lot of people, data engineers like myself, people who do data analysis, will often put the label of data scientist on themselves. But if they're the data scientists, then I'm not sure who the people are that are actually understand those other things. I can do some of that, but I'm much more comfortable and generally focus on that data engineering space. I really like that space. And in the machine learning space, I can do a lot of it. I typically would rather use something like AutoML, which I'll talk about maybe a little later, and we will see in this series, which you just kind of give it a lot of the parameters, and then you let this automated process try to find the best model. So anyway, machine learning, though, I'm going to say is typically done by statisticians, data scientists. And by the way, statisticians, in my experience, and researchers who use things like that tend to like R, programming, a lot. They tend to like that language even over Python. Data engineers like me tend to like Python better, probably because it really supports data engineering really well. So in the machine learning phase, you do model training and evaluation, and we do model deployment. So we train our models, and I'll talk a little more about that. I'm going to break this down, and we do a deployment. So in the analysis, you might have someone, if it's a team of people and it's a big project, you may have business analysts, you may have domain experts, like they really know the business side well, things like that. And then the data engineering piece, which is really the heavy lifting of getting the data prepared and getting it where you need it. It's a huge space. If you're looking like where should you focus, if you want to get a career and be secure for at least the current times, I think data engineering is a really good space. It pays well, it's in high demand, and there's a lot going on there. And finally, machine learning, which is typically done by a data scientist. Oh, I wanted to call this out also. When you kind of gone through this process the first time, parts of these steps will be created as what's called a pipeline. In ETL world, very similar thing. You have this sort of ETL process, and you put it into a pipeline, they now call it as well, and it gets the data from its source, it transforms it, cleans it up, massages it, munges, and finally puts an output data set. The difference between this and, say, extract, transform, load, the typical thing that's been done in business intelligence for decades, I guess, is that we've extended it now to include the model training, the data science end, which is the feature engineering, the model training evaluation, and model deployment. So we'll talk about that in more detail. But you'd pull some of this, not all of it, but I do want you to get the sense that we're going to need to automate this, because we don't just do it once and say, great, that was good, let's forget about it. We now have to take our model, and models basically they have something called model drift. The model may work now, but as things shift, the data changes, the world changes. A model that predicts really well in one day may not predict well 2 days or a week from now. And so you have to go through the cycle of pulling data, retraining, and redeploying models on a fairly continuous basis, regardless of the model, just the specifics, like how often or what change. So there will be this sort of extraction from this, so you're going to want to write your code fairly well and probably extract directly from these pieces something that would be an automated job that will kind of run on a periodic basis to refresh this whole thing and that type of thing. But the first time through, you're just kind of carving out the path and getting to the end goal. So let's start with the first phase, analysis. So we have identified the use case. Here's where you really want to ask lots of questions. This is actually one of my favorite spots because I love test questions and I can just drive people crazy. You want to do that. Document everything. Throughout all of these processes, take notes. Write it down. If you don't like taking notes, if you don't like documenting what you're doing, don't go into data science, please. Personally, it's not good. A lot of mobile app people, you can get away with that. Developers, programmers typically can get away without taking notes. In a data-centric side of things, you want to take notes. You want to make it clear. To be honest, it can be a little bit of CYA in a sense, because you can say, well, this is what I asked, and this is the data we agreed we're going to use. And you may find if there's a problem, at least you've documented everybody what you're saying. But more importantly, there's a lot of information you need to be clear about here. And by the way, I've thought about doing videos specifically around analysis and running interviews. I've done this so long, and I'm great at coming up with questions. I don't know if other people find that to be a challenge, but if you're kind of wondering, like, wow, where do I start and what should I ask in an interview and how do I do this? Put notes down there, and I'll see that if I see people are interested, I can go into doing that. It's definitely one of my hot spots. But this is the stage where we ask, what's the problem? What are we trying to get to? Is it a predictive model? Is it face recognition? Is it fraud detection? Is it just understanding our customers better and getting insights or pretty graphics or whatever? Really want to get that down, and very often I find management doesn't really know, and you really have to guide them because they may have a very broad definition. We want to know everything about anything that ever existed and double our income, which is not realistic. So expectation setting is really important here too. Like, yeah, we'd all love that, but how about we just go for 10% increase in sales or whatever we can do? So you want to gather information. I always send meeting summaries back to everybody. This is what we said, to document. You want to define the scope of the project. And again, this is common to any IT project. In particular for the models, what's our accuracy? If you're trying to predict, say, a model that identifies a rare disease that occurs in 1 in a million people, a 99.99% accuracy is useless, because just say no every time, you got a great model. So accuracy has to be determined very specifically to your use case. If you're trying to do something like predict a product a customer's likely to buy, and you have 5 products, sometimes even in there, you'll have one product that 80% of the customers buy, which means you're going to have to make sure you're getting at least a 90 to 95% accuracy to make it better than just guessing they're going to take the 80% product. So those are things you have to think about. It's not always simple. People tend to think, oh, I just get better than 50%, but that's actually not true. It depends on the use case. You also, how much time do we have? Sometimes managers are like, we need this in 2 days. Not going to happen. So good to know. Start looking for a new job. Just kidding. Cost constraints. Do we have cloud resources? Do we have, how many people do we have? Like the team is a little further down. What can we spend? How do we have, can we use like Azure or AWS with lots of resources? So cost constraints are good to know up front as well. What are the assumptions? Big assumption typically is we can do this, which may not be true. And a lot of times management doesn't understand. When I worked at Microsoft, I had a lot of customers that think that machine learning was just magic. Wow, you just give it a few things and woof, it comes up with this magic for you. And it's not true. It requires a lot of work. It's a lot of diligence. And if you don't have the right data, you may not, then you may not be able to do it. But the first time I ever tried something with analytics was doing web logs, and they wanted to do things around the products that people were clicking on, and they never tracked in the logs the product codes. Couldn't do it until we started tracking product codes. So these are important assumptions. Assumptions can be how long it'll take, the complexity, on and on. So you want to make sure you get what are the assumptions here. Again, the team, how many people do we have? How much time do we have allocated? And again, document. Write down what you need. You can use Jupyter Notebooks to capture a lot of things, especially during the analysis for documentation. You can use, emails. There's a lot of different resources you can use to document. You can use just Microsoft Notes or different things. But whatever it is, just document it and share and all work together. Now, in the next stage, identify the data required. This is a key part because, okay, you want to do something with sales. Where is the sales data? Do you have sales data? Imagine somebody wants it. We want to do this with sales data. And it's like, where is it? Well, it's actually in a third-party system somewhere else that we have no access to the data. It's like, well, then we get back to assumption. Not going to happen. So you have to think about that. Maybe the other thing is very often you have multiple systems. You've got systems like, say it's insurance, you've got a claim systems over here, but that's commercial claims. And over here you have, say, personal claim systems. Maybe several different types of commercial claims. So these are like, maybe life insurance claims, and these are auto insurance, whatever it is, or sales systems, different systems. So you need to identify what are all the different systems that apply, if they do apply. Are we getting data? Let me clear that. Where is it coming from? So it could be, general data could be coming from the internet. We could be getting data from a service that we pay for, the company pays for, and things like that. We also, once we get through the idea of identifying the data required, we want to get a sense of like, and this is preliminary, we're not into maybe looking at it, but how good is the data? It's like, well, we got a new system 3 months ago and we've got data for that. It's like, okay, what's before that? It's on paper, like, okay, problem. So these are really important. Take some metrics too, because very often this will tell you a lot. If you talk to somebody and you're doing a project and they say, well, we have like billions of rows of data and 40 tables and stuff, you might think that's bad. Actually, it's probably a good sign because probably the data you need is there somewhere. But you might find that they say, oh, well, we've got a few spreadsheets and it's 60, 70 rows of data and you're trying to do sales forecasting. Again, you really don't have much to work with, and that's where you need to dig deeper and say, well, what else can we do, etc. So you got to identify what is the data, where is it, how good is it at a high level. If you're dealing with data like healthcare, there's a lot of regulations on, especially in the United States, on privacy. So you want to make sure that if you can possibly avoid it, and most times in this type of thing you should be able to, avoid taking personal identifying information like social security number, obviously, but names, addresses. Try to genericize the data as much as you can. Maybe even aggregate it to some level. If you can, it makes it easier to process. And by aggregating it, you lose that ability for someone to trace back, conditions, etc., to a specific person. Similarly, things like credit card data or bank information, very sensitive data. You have to be very careful. When you're doing data science, you tend to be pulling data out and putting it somewhere that is not as secure as the system of record, and that can be a risk, and you have to be very aware of that. And personally, just to avoid taking stuff you don't need. Real important. A lot of people don't do that. Okay, so that was that stage. Now let's go into that data engineering stage. Data collection. This is where you're going to pull the data from wherever it is into your project. By project, now if you're talking about Databricks, we're probably about talking like pull it in from SQL databases, Oracle, any other places you have, and maybe flat files, etc., and bring them into a Databricks database or a Databricks set of systems. We'll create SQL tables, and there's various ways we can do that. So we're going to pull the data together and bring it into probably now, remember with Databricks, we have some sort of physical storage in the cloud, virtual physical storage. So in Azure, we have blob storage, AWS, whatever they call it. I forget what they call theirs, but the storage is there. So you can put the data there. They call that staging it. You bring it in and it's available to be used. With Databricks, it doesn't need to be physically loaded into a database, but we can still query it with SQL, as we'll see. So pretty good. But the idea is to kind of consolidate the data, pull it together, and put it into a staging process. At this point, you just want to know you've got the data you need and it's somewhere it can be used. Data preparation is sort of the next step. Okay, we got the data. Can we use it? That's a kind of a big question. Here's where we want to take the data. We may have a lot of null values. We may have a lot of missing columns. Sometimes, many times actually in systems, there's columns they just don't use. And you're like, boy, that's pretty good. That's the birth date of the person. I can use that to get the age. Yeah, we don't fill that in. It really all depends what the requirements are when they're doing the system. And just remember, the source system is not about querying an analysis. It's about doing a job. It's like this is a payroll system. It's there to get the paychecks out. They don't really necessarily care about the demographics of the employees. And even customer systems typically may not have details you might think would be really good to have. So just be aware of that. Identify problems in the data and gaps. So bad data, maybe sometimes, and this happens, believe it or not, systems go down. Oh yeah, for 2 weeks we couldn't use the system at all. No records at all for that period. And you just get this weird gap, and it happens a lot in systems. You'd be surprised. So that's another thing. And again, you might have multiple systems to pull from, and it might be that, well, we have different systems in every region. So each region has sets of data and slightly different. So you need to consolidate it. You need to get it into a consistent format. And you need to restructure it in a way that's intelligible and makes sense. In a sense, what you're trying to do, what I would do in this case, is try to create a sort of localized data warehouse. It doesn't have to be dimensional. That's overdoing it. You don't need to get that fancy. You just need to make sure you have the data structured in a way that you can query it and use it. So you need to make sure you have, for instance, if you're going to use tables, which we'll be doing a lot of, you want to make sure you have columns that can relate one to the other to do joins, right? We've got a customer ID here, and there's a customer ID on our sales record, so we can see who bought it. And then on the sales record, there's an invoice number, and that gets us to the invoice data. So you want to make sure you have all of these things. Now, once we get through the data prep, we've gone through this. Now we have data we can start to really make sense of. We're going to have fun at this point because we can do exploratory data analysis. And as the word kind of makes, or the words imply, you're going to be exploring, you're going to be looking around at the data. It's iterative. I like this kind of stage. I think it's kind of cool. I'm not really typically the business analyst, but I'll do some initial stuff. But you query against it, so you might join like your sales information back to customers, and the customers have demographics, and you can find things out like where do they live, what are the ages or age ranges of customers of different products. So you might say, oh wow, certain age groups tend to purchase certain products, whereas other age groups buy something different. Interestingly, maybe we have geographical things. We may operate in 50 states, and yet there's certain states that are really our hotspots. That's where we do most of our sales. Typically in anything, there's always that 80-20 rule. 80% of X is here. So it might be like 80% of a certain age group is our sales or a location. So you want to see what patterns can you find. And this is kind of cool. You might find that, for instance, people who have a certain education level tend to gravitate towards your products or towards certain products. Now, here's a point where you can kind of iterate again over data issues, data quality issues. You might get into the exploratory data analysis before you realize, like, wow, there's something missing. I'm trying to do some analysis over, say, months over years, and finding out several months are not there. Maybe I don't have complete sets of information, etc. So you want to do that. And when you hit these roadblocks, as soon as possible, you want to raise that to the business side, whoever can help you to resolve it, like to get the data, what you need. In any IT project, you want to Identify problems as early as possible and raise them as early as possible. The worst thing you can do, everybody does it by the way, but I will tell you don't, is to push off problematic questions or issues early in the project to later. Oh, we'll deal with that later. Oh, we'll deal with that later. That always burns a project, and the later you wait, the more you've built, the more expensive it is to correct a problem. Case in point, I said, remember we're missing this product code. Imagine nobody thought about it. Nobody even asked that question. So you get all the way through into your exploratory data analysis. You spent a lot of time and money, and management's promised the world we're going to have something to deliver. And now you come up and say, oh yeah, you know that thing you wanted to do around products? Can't do it. So you really do have to watch this. One of the number one project problems I've seen over my many years is not really nailing down each phase before you move on. There's a huge tendency in companies, and this is just general, not anything specific to a company, a huge tendency to just kind of say, yeah, we're good, move on, because they want to just get to the next step. It's always rush to go forward. But again, if whatever is dropped in one phase, you don't want to discover it later because it's going to be much more expensive to correct. Okay, that's my soapbox. And again, a key thing at the exploratory data analysis phases, this is where you want to make sure you really have what you need to solve the business problem, to really meet the goals. You may get a lot of great stuff, pretty graphics, dashboards, awesome, but maybe you're saying, yeah, but we don't think we have what we really need here, and you might need to go back to the drawing board on that. And finally, assume you have what you need, you go into a feature engineering stage, and this is where you're going to look at all this data. For instance, maybe you're trying to predict, I like healthcare examples because I think it's very intuitive, but you're trying to predict who's likely to have a heart attack. So you look at the demographics, yes, like the age, possibly where they live could affect this, biometric information, what's their blood pressure like, have they had past heart attacks, pretty good indication, right? So things like this, these different types of attributes can tell you very strong indicators they're likely to have it in the future. There's no real surprises, I think, most of the time in feature engineering in the sense that certain characteristics drive decisions, but you need to make sure, you need to start thinking about what will drive this particular solution. And you may find that, again, this is tricky, but you may find as you start to do, actually try to do models, that you're not able to get to the accuracy you need because you're not getting the right attributes necessary to predict to that level. In other words, if we're trying to predict if somebody's likely to have a heart attack, but I don't even have the blood pressure, I may just not have a good predictive model. So I may need blood pressure, I need age, I need BMI, the mass index, all that cool stuff. Finally, we get to the part where I hand it off, right? We go to a data scientist. The data scientist is going to do model training and evaluation. Now, what does that mean? Now, again, this is not required. The model side of this is typically part of the data science process, but you can get a lot without that, and you can do lots of applications. IoT and dashboards don't require this. But if you're going to do model training, and this is a tricky area in the sense that it's very broad, so I tend to think of this in terms of predictive models. We're trying to predict sales. We're trying to predict a product somebody will buy, etc. But there are many. We've seen image recognition. We see things when we talk to devices that can talk back to us. We have all kinds of AI type things. So it's tricky to say where in all of this would fall. But in a typical data-centric flow, this seems to make sense. And I'm thinking along lines of columns and rows of data to drive this versus something like images and video feeds. So kind of drawing this. But this is the idea. We're going to get to model training. So typically in predictive model, where it is data, rows and columns, you split the data into a training test set and the test data. What do I mean? So you have maybe 1 million rows you've got. You would take roughly 80%, we'll just say, some percentage, large percentage, and take that part and you split it and you call that's our training set. And you feed that into the model and you give it the answers with it, by the way. So you feed it in and you feed it the column that will tell it how to learn it. And what happens is that the data science, the machine learning algorithm, this is what we call the model, the machine learning algorithm creates a correlation between all the input attributes and the results you're trying to predict. So let's say you're trying to predict somebody who's likely to have a heart attack, and you give it 1 million rows of medical data, different patients who had, yes or not, did or did not have a heart attack. Well, it looks and says, okay, well, people of this age, over a certain age, people with certain BMI, certain blood pressures, etc. It finds that when it looks at these combinations, it says that's a very likely person to have a heart attack, and it may predict they're going to have a heart attack. Somebody else at 22, no problems here, no history, not likely to have a heart attack. So those are the ways it predicts. Different models have different ways of getting to that answer. And I'm oversimplifying it greatly because there's all kinds of models, as you may have heard. You may have heard of things like deep learning, neural networks. You may have heard of there's all different kinds. There's all kinds of ways to correlate and do that. But the bottom line is, so first you give it a test data set. You give it a training data set. And it goes through and tries to figure out, it has the input columns and it has the output column, what you're trying to determine. And it maps it. It says, okay, I'm going to build an engine that can predict this with data where I don't know the outcome. Now the testing data is something you hold to the side, and after it's generated this model, and that's what model training is, you're creating a program. So the strange thing in a way with data science is you're creating a program. Your output isn't an application. You're actually putting everything together through data and then pushing it through a program, and that program is going to create another program. And that program is your predictive model. It's called a function because it's all self-contained, but it's a program, right? And now that you have this function, you say, great, I have this awesome function that was output from my model training that will predict whether someone's going to have a heart attack. I wonder if it works. How do I know? Well, I'm going to have to put something through it, aren't I? I need to try it. And I probably don't want to try it in production where people will die if I'm wrong. So I take a subset of the data, the stuff I pushed aside, I call this my test data set or testing data set. And that's usually 30 to 20% of the data that I didn't give it, right? Did not go into the training. And I now take that and I feed it only the input columns. I do not give it the output. So I'm saying predict this based on input only. And now it's going to go through and say yes to this person, no to this person. Yes, they'll have a heart attack. No, they won't. And it finally comes through and I have an answer. I have a whole list of what it predicted. It doesn't know the answers, but it's using in the model. And then basically I can compare what it predicted to what the reality was because I held that. I know what it really did. This is historical data. And then I can determine how accurate was it? How often is it accurate? There's many ways to sort of get to this. I'm simplifying it. So in a true false case, what I said is good. It works really well. But when you're doing other types of models where it's a range of accuracy like sales, sales forecasting can be different. But the idea is, how accurate is it? Is it good? So that's where the testing data set comes in. So again, you split it. You may need to do data sampling. This is something that took me a while to get my head around. But when I was actually doing my book, I had to kind of look at this more because when you're trying to predict something, imagine you're trying to predict whether a customer is likely to buy a product. And 95% of the sales in that company is, the widget A or whatever the product is, the exocclutron. Well, the models are actually kind of like people, if I can pick the easy way, I'm just going to go with that. So it looks at the data and it realizes, wow, 95% of the time, the person always buys this product. So it's just going to say, there you go, 95% accuracy, just say this product every time, which doesn't really help you, right? That's not too good. That's why we get back to what's our required metric to be successful. So in this case, you may have to resample the data, and what you do is, in one option here would be to distribute the data so that it looks like people buy all the products at about the same amount, same rate. And in that way, it can't rely on that factor alone to predict the model. It says, oh, okay, now I don't see that. So I'm going to have to say, and the data actually based on different attributes, age, education level, salary, income, whatever, determines now what they will buy, and then you try to get something. So sampling is a key thing. This is also a case where you need to figure out what kind of model do you want to use. Are you going to go for the slick new PyTorch and deep learning neural networks and whatever else there is? Are you going to do more simple models? There's all different kinds of correlation models. I don't know, deep forests and all these models you can use. But there's a lot of different ones, and there's simple ones like linear regression, really simple, to more complex. I favor simple first, but right now the deep learning networks are extremely popular. But whatever you're going to do, you need to sort of figure out what you want to do there. And you will often, a data scientist will usually pick a number of different models and techniques, sometimes even combining models that can do that, like layer them in. It's pretty cool. And then by doing that, comes up with, runs them through, and then we'll compare, called scoring. It compares the effectiveness, the accuracy of all the different models and says, this is the most accurate. This one has other values. Now, sometimes in this, if you're like me, I would probably try to throw it into something like auto machine learning, where I give it a range of tests, a range of models and things to look at, and I give it the data, but let it go through and iteratively just try all these different models and permutations. There's factors in there too, which are called like setting hyperparameters to models and things like that, which gets complicated as well. Like what these are parameters, just like function parameters, but they're fixed parameters that control how the model generates things. So there's a lot of things that go into this. In the end, you pick the model. What model, or what several models if you want to keep looking at them, but really pick the model that you think is the best one. It's going to work. You may have to go to management and evaluate, and sort of that's where dashboards and whatnot can come in handy to say this is why this model is the best one. And you also have to know, like in many cases, if you're in a controlled industry like banking, you got to make sure you're not violating laws, because if the model happens to be doing something like picking people based on zip codes where they live, or in somebody like personnel, they're trying to pick who we should hire, and you're doing it based on, say, past data, it might have discriminatory effects already built into it, so you have to watch out for that. That's where data scientists really important. And finally, you got your model. This is a program, as I mentioned. This is something I think that's easy to overlook, but it is a program. Now, here's the thing. If you got nothing else out of this, this is good to know, because it took me a while to get this to my head, but there's a big difference between training a model and getting that model and then using the model. We tend to think, for instance, Databricks is a good example, Apache Spark, the underlying engine, right? When you're training models, you might have, petabytes of data. So you're doing genomics, we'll say. You might have really large volumes of data to train the model. But once you have the model, it's like a little lightweight program. It's like a little function. You can put it in your pocket, trade it with your friends. So as a result, you're not going to want to deploy a model on Spark. I personally can't think of a good reason why you would ever deploy a model on Spark. Somebody could probably tell me. But typically, now that you have the model, the heavy lifting is in the training. Now that you have that function, you want to put it somewhere. It already knows how to do what it's doing. It's not being trained anymore. So you want to take that program and maybe deploy it somewhere. So we have things like maybe Kubernetes, or in a VM somewhere, or wherever you want to deploy it. In SQL Server after 2016 and beyond, they have a machine learning server in there, and you can actually deploy a model on the server and then call it from like a stored procedure to score data. You can instantiate and do things like that. So there's lots of options. In a Databricks situation, there's a part we'll get to where we can talk about using Azure ML, and you could actually in Azure deploy it to Azure ML. AWS, I'm sure, has their version of that, or you can deploy it to a container, or you can deploy it to a VM, or you can just really put it wherever you want. You could deploy it, even take the model and deploy it on AWS from Azure, or vice versa. So once you have the program, it's do whatever you want. The key to there is you need to know, how is it going to be consumed? Is it going to be internally used only, maybe sales forecasting? Is it something like a web app, mobile app, where it's a healthcare type of thing, and then based on the data, it's going to come right back to the person and say, here's your score? In those cases, then you want to make it probably something that it can call through a REST API and bring the results back, etc. So deploying is a big piece of this. The model deployment may actually get into a different type of person than the data scientist. It may get into more of a DevOps developer side at that point. More likely it would in the case of like a mobile app, right? Because the developer is going to need to know, how do I get this? How do I call it? And they're really probably more skilled in the level of deploying to containers, etc. So somewhere between DevOps and a developer, you probably do that last phase. And finally, post-deployment. This is where you've got this whole thing going, and you're going to put that pipeline. I should have a bullet there for this, but put that pipeline that's going to iteratively pull data in, reanalyze it, featureize the data, transform and create your features, and then put it through model training, and then maybe do even more comparisons. Is it performing to the level you want? And then deploy it all over again. So that is typically an automated sort of job. They call it pipeline, machine learning pipeline. It's getting better and better, but that is still evolving. And part of that, so you want to monitor the model. How's it doing? You're going to have potentially dashboards and visualizations. But you got to keep doing that, because otherwise the model will start to get old, and it will start to get out of sync with what's really happening in the real world, and your results can be really bad. After a while, it's predicting terribly, and it's going to be not doing what you need it to do. So that's your post-deployment. So we talked about a lot. I hope this is helpful. This will lead into the structure of the subsequent videos I'll be doing, because I'm going to be laying things out according to that overall data science process. So we talked about what is the data science process, and I really want to say that it's really just a sort of way to sort of frame the steps you need to go through to bake a cake. In this case, your data science cake, right? So you're going to analyze where's the data, do the initial stages, get the data, clean the data, all this stuff. So you need to follow it through. So we talked about those steps, and we're going to see them in more detail as we go through the other videos, but we'll see more of that. And finally, we did a sort of in-depth look at those steps. So I'll put some links below to cover some other things in here. I can't remember what yet, but I'll put the link at least to the content in the slide so you can go look at those. I'll also put a link to my book so you can go buy it because it's riveting. And I think that's covers it. So I want to thank you. Please subscribe, share, like, and make comments. I always like to hear comments. Good comments are always happier, but critical comments, as long as they're meaningful and you can tell me what you think about it, that's great. I always look forward to getting things that can help me improve as well. So, till next time, thank you.